All right. Hello? Same issue. Okay, that's off. All right. Good morning. What's wrong with this thing today? Hello? No? None of these seem to be working today. Hello? Okay, good morning everyone. Sorry I'm running a bit late today. There seems to be some issues with the microphone, so I'm just gonna have to speak into this one here. So shout out if you can't hear, or if you need me to repeat any part. So yeah, today's our last lecture about computer networks. So we've been through the entire stack of layers, and we finally arrived at the topmost layer, the application layer. So just to summarize our journey here so far, we started the physical layer. We've learned that the physical layer is responsible for moving bits across analog mediums. We've talked about different types of mediums, and the physical layer's job is to provide an abstraction to the data link layer so that the data link layer can provide reliable point-to-point communication regardless of the underlying physical medium. Sorry? Yeah, I will try. I will try. I can try these again. I don't think this will work. Is that working? No, it isn't it? Is it? Well. It's not really an option to all this, but maybe if I sit down. I don't like to sit down. Okay, maybe that's better. Yeah, okay. As I was saying, data link layer provides or gives us reliable point-to-point communication. And provides an interface to the network layer such that then the network layer starts to look at the point-to-point communication across wide area networks, long distances, and provides routing and basic congestion control, and encapsulates packets into IP packets and provides a connectionless way of moving information across the network. And then the transport layer builds on top of that by providing a reliable point-to-point communication over long distances using reliable TCP connections. So we finally arrived at the application layer, which is the most common interface that users and developers see. So web developers interact at the application layer. So it often deals with presentation or session layer issues. If you go back, you see that the OSI model, the presentation session models layers are actually sort of skipped over, whereas in the TCP model they're sort of brought out all together into one. And it's because in the OSI model they're often sort of very minimal layers, very kind of thin layers, which don't have sort of enough material to talk about. So the TCP IP model tends to be sort of a set of protocols which are more commonly used these days, and so the application layer sort of brings those all together into a single sort of unified layer. So it allows sort of users to build what we know as web applications. It contains network services as DNS, domain name system, as we will see, and other common applications you've learned to work with across across your upbringing, mine as well, with email and browse and the web. So we'll talk about these today. So DNS, a network service, and that's sort of an auxiliary protocol that makes the internet or makes more usable. Then we have email, of course, and web browsing as well. So at email, we'll talk about SMTP, POP3, and EMPA protocols very briefly, just so you get an idea of what kinds of application layer protocols we tend to see, and I guess most importantly, the HTTP protocol at the web browsing. That's probably, if you're a web developer, you'll encounter this protocol through and through. So let's talk about DNS first. So DNS stands for Domain Name System, and the idea is that we've talked about how IP addresses can be used to sort of uniquely identify any network or computer or machine across the internet, but we're sort of really bad at remembering IP addresses, but we're much better at sort of remembering names of things. So the idea of DNS is that you'll be able to remember a name such as google.com, but you're not going to be able to remember the IP address. So you need some sort of system that translates names into IP addresses, because that's what your computer is able to needs in order to communicate. It needs the IP address, so it puts that in the IP packet, and all the routing and all that transport stuff we talked about are able to work through, and your request is able to get to the final destination. So yeah, the domain name system sort of provides a translation process that allows names to be converted into IP addresses, and not only because we're bad at remembering IPs or numbers, long sets of numbers, but also because this can change over time. So it's much easier to refer things to names that don't change than to IP addresses that are sort of susceptible to changing as well. Right, so web browsers interact through the internet protocol. So all these services are mostly built on top of TCP connections, because we sort of need reliable data transfers rather than on UDP. And yeah, so the browser is a piece of software that allows you to browse the web, as you know. So in the browser you input the domain.com or whatever, and sort of name you want to access, and in turn that communicates with the DNS server, as you see over here, which gives you back the IP address, and then so the browser has the necessary IP address to make a request to the web server, who in turn returns a sort of a web page which you're then able to view in your browser. So we'll talk a little bit about the web further, but the key point is this: DNS is responsible for translating domain names to IP addresses. And the DNS namespace, so you can have many different types of names across the web. You can, as you know, you can have .com, .co.uk, and these were built in a hierarchical fashion. So starting with the root, which is often omitted, it's sort of divided into zones, and of course you'll have, it says at least one DNS server exists in each zone. In fact, you'll have many, because you need redundancy across the web. You can have a single point of failure, because if you only have a single DNS server, it can be easily overloaded, or if it fails, then sort of the whole internet breaks down. So this is one of sort of the core services necessary to make the internet run as we know today. And so you'll have DNS servers sort of spread out throughout the entire internet, and you can have local sort of DNS servers, and you can have more global DNS servers depending on which level of the hierarchy they are operating at. So the idea is that eventually this forms a tree such that each DNS server knows about its children, or all hosts in its zone, and its parents. So you might not know about other DNS servers at the same level, but you'll know about the end parent, you'll be able to communicate with your parents and with your children in order to eventually arrive at or search for the domain name that you're looking for. And I think this is just an example of different DNS root servers. It's not really for a member, it's just for your sort of benefits. And I guess as it started, we had the single server for each of the 13 IP addresses, while today we have a server cluster for each of them. And the reason why is that we need redundancy in case one of the systems or the machines breaks down or is the subject of attacks. Then you need redundancy, you need the machines to be able to step up and fill that role. And also for the because you need load balancing, so you might have loads across the internet which change across the day, so you might have periods of the day where you have busiest traffic, so you need to be able to scale up and have systems ready to serve those requests and enable the internet and the web to be usable as a whole. So the process of translating an IP address to a host name is called resolution, and in order for this to work, two machines need to talk the same language, and again it comes the name of protocol, so they need to be able to speak the DNS protocol. So in this example we have our machine who wants to find out where host B, which he knows by the name of robot.cs.washington.edu is. Oops. So what it does is sends a query to the local DNS server. So as we saw, we can have DNS servers at different levels. We'll first send the DNS server, the DNS request or query to the closest name server. So in this case, the host A being at filts.cs.vu.nl, it will send a DNS request to cs.vu.nl, the local name server. And if that local name server doesn't recognize host B, because it's sort of a different level of the hierarchy, then it will need to talk with the other DNS servers in order to figure out what host B is, who host B is. So here we'll talk to, in this example, we'll talk to servers across different layers of the hierarchy. So it goes up, all the way up to sort of the edu. So in this example, we have our server here, and it sort of talks all the way up here, and eventually it's able to talk to the DNS server on this side in order to eventually arrive at the robot machine. So the way we do is sort of traverse this tree in order to get to the necessary name server. So this is sort of the example that you have here. And we sort of have two strategies where the local name server sort of does all this for you, but this in a way can put too much load on the single local servers. So sometimes what can happen as well, I don't really need to know this, but it's just you get an idea of things can work. So the local DNS server will send so that the results of this query back to the originator, and the originator will try to query each of the domain servers in turn, rather than being the local name server in charge of this. So you can think as in the local name server returns sort of the IP for the name server up the hierarchy, and then the originator will go through these different iterations until it finally gets to the sort of desirable name of host B, or the desirable IP address of host B. Is that clear? It's a long-winded explanation, but the gist of it is the sending machine who's looking for another machine might end up speaking with a bunch of different DNS servers in order to arrive at the IP address of the host he wants to communicate with. And sort of one strategy that can be used to optimize this process is to use caching, so the queries can be saved locally and sort of reused for future searches or for future requests, including sort of partial answers across that. If it's sort of a long request and you need to contact other machines, you might include those partial answers in your cache as well, so you don't have to, go all the way to Washington or Edu every time you want to learn about a host in its zone. Right, so we talked about DNS, now we'll talk about email. So email, I guess you know email as well as I do, but so this is sort of a brief overview of how things work behind the scenes. So we typically you want to send an email to someone, so you're the source host and you're running some kind of software which allows you to write and send emails, and that's called the user agent. So that's a process in your machine, like Microsoft Outlook, which allows you to draft the emails and then send those over. So those don't get sent directly to the destination machine, so they get sent to a mail server, which is in Microsoft premises or on the cloud. And in order to do that, this is called a push protocol. They use SMTP or Simple Mail Transfer Protocol to push email from your machine to the mail server. And you can have a range of mail servers sort of distributed across zones in the planet, and they might then push those email notifications or email to other servers in the different areas which are sort of closer to the destination hosts. And eventually then, as you'll know, the process on your machine, whenever it's trying to find out whether it's more email or not, it's sort of running a process in the background which is sort of pulling periodically notifications from the mail server, and it does so using POP3 or the EMAP protocols, so Post Office Protocol or version 3 protocols, and the EMAP protocol is the Internet Message Access Protocol. So this would be a pull protocol, is the protocol that machines use to find out if they have any mail addressed to them and that they need to retrieve so this is run by the user agent so that they can show them those on the machine to their user. So SMTP is used to push email into the mail server, and EMAP or POP3 is used to pull email from mail servers into your local machine, into your user agent. Right, so, and these are called transfer agents, sort of move messages from the source to destination, so they operate behind the scenes. Right, any questions about this bit? Right, so as you know, so messages need to be formatted, and they typically use a standard form. RFC stands for request for comments, and it's how things sort of get technical specifications for the web. So you've seen different RFCs maybe mentioned before, and these are just sort of different technical standards that have been adopted by the internet. And in this case, this one is sent by the user agent to be handled by the message transfer agents or of the mail servers. And again, as all protocols that we've seen before, there'll typically be a header. So in your email address, you can specify who you want to send your message to. you can specify secondary recipient, so carbon copy, or you can specify blind carbon copies, so that's people who will get the email but not know about other people who've also received the email. And then you have other fields in the header which sort of help you specify any metadata and allows user agents to pass the email to look for this information and send it to the necessary or the adequate addresses of people. So very briefly we'll look at each of these protocols, though you don't really need to know this for the exam, or you don't need to know this for the exam, but it gives you an idea of how these protocols work and how different the application layer protocols have from the protocols that we've seen before. So in this example, at the top, we have a source, so the user agent that the host machine contacts. So the transfer agent, so it says, it misspells hello, abcd.com. The mailbox says that it's ready. A source identifies itself here, mail from Eleanor at abcd.com. The mailbox accepts. Then the source identifies the recipient, says okay, and sometimes you need this because as you know, your email sort of puts things in the junk and spam, and it's sometimes based on who the recipients are, so you need to be sort of an accepted recipient, or your email needs to come from a recognized domain so that it gets through those sort of security checks. And so 7, then negotiate any further parameters. So in this case, the mail server is send an email which ends with a dot on a line by itself, and so then the source sends the whole email, including those headers that we've seen, and then in this area here we have our text, which in this case is of a specific type. So text enriched, it means that you're using sort of markup text. So that means you're using commands such as bold to emphasize or define how your text should be formatted, how it is formatted, and how it should be displayed. And then we have further sort of headers or trailers, and then we have the mailbox accepts the email, and that sort of terminates the conversation. So that's SMTP, that's to push the email to the mail services from the user agent on the originating machine to the using the user agent. And POP3 is a different type of protocol. It's used to pull email from the mail server to the destination machine. So in this case, it begins by the destination identifying the user. The mailbox sort of recognizes the user, is a valid user, and the destination supplies the password, vegetables. The mailbox accepts the password, so there's an initial authentication phase, and then the destination requests the message list, and the mailbox sends the message list, and the destination maybe also requests specific messages. So you'll get a message list, and then you can request specific messages, and you can also put in requests to delete messages from the mailbox that the mailbox doesn't get cluttered over time, and eventually sort of terminates the conversation. So yeah, just 2 examples of interactions using these protocols, but these are not going to be in the exam. So, but they're here just to give you sort of an additional information or benefit of how these things work. So this is, I would say, this is the most sort of important slide here to look at. As long as you understand what's going on here, that these do not communicate directly but via mail servers, and they use each of these protocols to push and pull information. Who are user agents? They're processes running on the host machines, and the message transfer agents are processes running on the mail service machines. That's kind of what you need to know. Okay, so we'll look at web browsing now. So the World Wide Web, you're very familiar with the World Wide Web. It was created by Tim Berners-Lee when he was working at CERN, so the Large Particles Accelerator, the largest particles accelerator laboratory in the world. And at the time, CERN was having issues, not necessarily issues, but Tim Berners-Lee came up with a proposal that would enable the researchers at CERN to share information more quickly and easily. So he came up with the idea of web pages which would display text that was hyperlinked. So that means text that can contain links that link to other web pages, so that you can follow those links, and sort of that creates an interconnected sequence of pages. So the web is essentially the product of this initial creation, and the idea is that you have web pages that are across different machines on the internet, and these are written in HTML, and that you can view those using a special piece of software called the browser. So back in the days, browsers were very simple pieces of software, but nowadays they're probably one of the most sophisticated and advanced pieces of software out there. Again, a page will contain links to other pages, and this is called hypertext. And you can also, and each individual piece of text or imagery or video can contain links. If it contains a link, that's called a hyperlink. So HTTP, it's the protocol that allows browsers to display information on the web page. So it kind of splits, again using commands, it splits the text from the formatting such that those can be passed individually, so that they can be decoupled. Otherwise, people might be formatting things in different ways, and HTTP sort of gives a common language or a common way of, actually HTML is a common way of displaying that information in the browser. So we have HTTP rather than HTML is the protocol which is used between machines to communicate and to fetch web pages. So if you're a host machine and you want to display a web page, you'll talk to a web server, you'll make a HTTP request saying, give me the contents of this web page so I can display it. And then the web server can accept that request, and it can send the contents of the web page back to the requesting machine, or it can deny, depending on any security permissions or lack of authentication. You can deny that request, or it can simply blow up entirely if it's not able to fulfill the request. And yeah, it's essentially a text-based protocol that again runs over TCP because we want our information to be reliably delivered. We don't want pieces of data or of text to be lost in the internet. So most of these applications will run over TCP. So the pages are named using URLs, short for Uniform Resource Locators. So this is an example. So you can see three paths in this URL. You have the path before the double dot and double slash, which specifies the protocol. So the protocol you most commonly use to browse to the internet is the HTTP protocol, as mentioned. But you also have other protocols as shown here. You can use FTP to transfer files, so that's short for File Transfer Protocol. You can use file to view a local file in your file system. You can use mail too if you want to send an email. And there's other different kind of protocols your browser is usually compatible with and can run. So the path after the protocol specification, so after the double slash, specifies the DNS name of the target host. So we've learned that in order to map these names to IP addresses, they need to talk to a DNS server, find out what the IP address for this particular host is, and then the third bit you sort of can navigate within that. Is how you can navigate within that hierarchy of web pages that can exist in a single domain. So it can be the path to a specific file name or specific location within that domain. So any questions about this bit? I think most of you are familiar with this. Right, so let's look at the anatomy of a HTTP request, or how you go from the intention to view a web page to actually viewing it, what happens behind the scenes to make that possible. So we have your web browser, that's called the client, and the web browser talks to a web server, and he makes a HTTP request saying, I want to the contents of www.cs.washington.edu, and the web server can respond with OK. These are the contents of this page, and the web browser can multitask, so it's capable of parallelization, so it can run many of these processes at the same time. Or in this case, what's actually depicting is at the same time that it's doing the HTTP request, is also talking to Google Analytics, sort of exchanging any information about what it's doing in this page. And again, in YouTube, you can also sort of use it to retrieve the content, or not necessarily web pages, but other sort of forms of media as well. And there's usually sort of a database that allows this. So if you make a request to YouTube to view a video, you'll have to retrieve that information from a database and send that data stream again across a TCP connection, so that then your client or web browser shows you the video. Yeah, I think that's the gist of it. Any questions here? No. Right, so let's look from the client's perspective. So the browser understands HTML, so that's short for hypertext markup language. And again, it's a type of language. Markup is just a type of text language that decouples the commands, the formatting commands from the text itself. And you have many different types of markups. You've looked at Markdown as well, which is a much more economic or different type of markup language. XML is that's another example of a markup language, which allows for data serialization as well. So the client, the steps it takes to follow a hyperlink. So it determines the URL and the protocol used, for example, HTTP. It asks DNS for the IP address of the server, makes a TCP connection to the server, sends a HTTP request for the page, for the index.html or a different page within that domain, and the server responds with a HTTP response, which, if it's accepted, will contain the page as well, the HTML for the page that the client wants to view. And then so the client then continues in this cycle of requesting other URLs as needed to display the page, and then it closes any idle TCP connections as it goes along. So it's sort of response to the client is responsible to not sort of grow out of control and sort of manage his own memory in a way that's not going to destroy the host machine. Okay, so we know that web pages can not only contain text, but they can contain other types of media. And traditionally, in order to view that media, you might need a plugin in your browser. So the most sort of significant of these for a while was Adobe Flash. So that allowed you to sort of view videos and on your browser. That eventually went away and gave way to HTML5 and other forms of viewing video on the web that were more efficient. So instead of having a plugin, you have a helper application. So that's a separate process running in your machine that talks to the browser and is responsible for displaying video or audio or other kinds of media. So originally, the web did not support those types of media, but eventually there were extensions to HTML called MIM extensions that allowed the browsers to support these other types of medias, and as well as emails. Actually, this relates to emails. So emails nowadays can show emojis and all, and you can add images and all that stuff, and that's because of MIM extensions. But I digress. That's not really important at the moment. So instead, let's look at the server from the server's perspective. So the main steps that a server takes to serve the pages, and these are not the only features that the web servers have, but they accept the TCP connection from a client browser. They go to the file system or to the database and get the path to the page, which is the name of this file requested. They'll get the resource, which is typically saved on disk, and then they send the contents of the resource to the client, as we've seen, and then they eventually release the TCP connection. And then, because web servers, depending on how popular the website is, they might need to use a bunch of strategies in order to optimize this process and be able to handle hundreds of thousands sometimes, or millions of connections at the same time. So they'll use caching, multiple threads, and other approaches to sort of be able to scale performance. But that's not too important to know for the exam. It's mostly how things operate from the perspective of the client and server. So we talked about how we can make different HTTP requests. So there's a number of HTTP requests you can make. So those are shown at the table at the top. The most common of which is HTTP GET. And as a user of the web, that's the request you will most commonly make when you're using your browser. If you're a web developer and you're developing web applications, you might come across other methods as well. Most commonly, you have get head to request a web page of a header, or the header of a web page. You have put, that's a request to start a web page, and you have a post, which is similar to a put but not quite the same thing. So post is more append, whereas put is you're replacing the web page with a new one. So if you're doing a form, if you're filling out the form on the web, and you submit that form, that's typically a post or a put request. And then you have other types of requests. You have delete, and you have other less made HTTP requests. The bottom three, you don't really see those often at all. And of course, you can make a request to delete the web page, but the web server is gonna just tell you, good luck. He's not gonna allow you to do that, right? So this works if you're developing your own web application, or if you're using HTTP to interact with an API. You might have access to methods like this, but otherwise you'll often use GET and sometimes put or post to submit forms online. On the bottom, we see the types of some examples of responses that web servers can make, and these are usually put into different categories based on their code. So we have codes in the hundreds or 200s, 300s, 400s, 500s. The first category has to do with information about the request. You'll often see 200 types of answers, which signify that the request has succeeded. So this is what the server answers when it's returning a web page to the client. And then you have error type of request. So if you're going to a domain server which you don't have authentication for, you'll encounter a forbidden page. So for example, on GitHub, if you've used GitHub before and someone sends you a link to a private repo and you try to access it without being a collaborator, you'll get a forbidden page or a page not found. The difference between the two is sometimes you don't want to tell the world that's actually a resource at that domain page, so you'll encounter a page not found rather than a forbidden page, so that malicious actors do not try and sort of overload your web server with the request to that page. So it's a way of not giving out information about your system. So the types of errors you encounter will be typically page not found, and those are for security reasons, even though you can also encounter 403, so forbidden pages, possibly on internal internet. Whenever you try to access a resource you don't have credentials to. Lastly, if a server sort of blows up and it's not able to fulfill your request, it will typically return an internal server error or a try again later. And this can be when the server is down or when you ask the server to do something that it doesn't know how to do. And as all protocols we've seen, we have messages, and the packet will also have headers. HTTP is no different. So alongside with the request, you need to provide some additional parameters. And so here you have some examples of message headers you get for request type of HTTP messages and for response type of HTTP messages. So some examples are host, where you provide the server's DNS name, you provide the type of pages that the client can handle, so that's the accept field in the header. From the server's perspective, the server can specify when's the last time the page has been modified, so the last modified field. You can specify the type of content and the length, the encoding, and all those things. We'll look at cookies in a bit. So the sender machine can specify the cookie which stores information about the host machine, so that you don't. You've noticed when you log into a certain website, that login usually survives for some time, and that's because there's a cookie or there's some kind of mechanism which is storing the state of your connection, so that you don't have to log in every time you're going to that website. And that's sort of used in a way to increase the usability of the websites, but also potentially for companies to get some additional data on your track. Oh, as I was saying, so the cookies can also be used sort of to track what users are doing and how. Right. So you can resume a session. So that's the key idea, is that you store state information, and I can resume a session rather than having to log in every single time. So imagine you'd close the web browser page and then you return to it and your login is gone and you have to go through all those steps again. So cookies allow you to save that information and other things. I don't know, if you're playing a game and you're keeping score, so the cookies allows you to save the score and sort of return at the same score. So those sort of things, because HTTP is a stateless, it's meant to be used as a stateless protocol, so no state is kept when you use HTTP. So the cookies allow you to record some state that's useful for some kinds of applications or websites. And this talks about two different types of cookies. First-party cookies, which are directly stored by the website you're on. And this is sort of where the privacy concerns came in, that about companies or storing, saving your information and then mining that information. And you have third-party cookies, which are transmitted to websites other than the one you're on. And these are called the tracking cookies. And you'll have lots of extensions on browsers sort of to block this type of cookies, which are sort of thought of as spies. Sort of they track your internet usage even when you're on a website, when you're on any website really. And these are done for marketing purposes, so that when it's time to show you ads, they can show you kind of specialized ads rather than just something generic. So now we'll talk about two different types of web pages. We'll talk about static web pages, and these are simply files. So all users will see the same page once they go into a specific URL. It can be, it can contain lots of things, text and images, and be interactive. But the key point is that a web page is static if any user that goes into the web page will see the same thing. And those static web pages have been typically pre-generated and whole, and the interaction sort of amounts to, give me that web page, and the server just finds out where that web page is on disk, retrieves it, and that's it. So it doesn't have to do any computation, additional computation, in order to generate new content. So that content has already been generated. Right, and as you know, we talked about HTML describes both the content and the formatting, but sort of across large websites it's hard to maintain a consistent look. So there's lots of web development frameworks, and CSS was introduced to help you stylize your HTML and your web pages with HTML.4, and that allows you to achieve a more consistent look and sort of scale, make it easier to develop your web page. And this just shows you sort of the the differences between different HTML versions, so how HTML has evolved over time, and the current version of HTML sort of supports all different types of resources and types of content. Namely, video was introduced with HTML5, so you can use the video tags in HTML to specify so the location of a video on a web page. So just to give you an idea how this has evolved over time, has sort of the needs to show more and more complex information on the web have evolved as well. So the second type of web pages are dynamic web pages. So these are generated on demand by programs running at the server, although they can, I'm not sure if she goes into the difference. No, okay, so I guess there's two different approaches to generating dynamic web pages. They can be generated at the server, or they can be generated at the client side. So at the server side or the client side. So examples of server-side approaches, you have PHP, which is really not so used these days anymore. You have other kind of server-side approaches, which use Python or Ruby or more kind of modern and friendly programming languages. And the idea, if you have a server-side dynamically generated web page, so there's the request, the HTTP request comes in the same way for a static web page, but the program will have to do some computation in order to, so for example, if you have a login, or if you have a web page that's specific to a user, that contains user information, or you might want to show information that's specific to that user or relevant to that user. So you need to generate that dynamically. You can have that pre-generated for every single user on the internet. So the program will generally need to speak with the database in order to retrieve information for that specific user or for that specific zone. So web pages can also be shown differently from region to region. So all of these things put together give you sort of a dynamic way to generate web pages. And then you have the approach which with this can be done at the client, since our machines are very powerful and these days and they're capable of doing computation themselves. Many web pages are embedded with JavaScript, which allows them to run some of the computation themselves rather than relying on the server to do everything, because if you want to communicate with the server, there's a delay associated. The message needs to be sent, needs to be propagated, the server needs to do something and then answer back, and that takes time. So JavaScript, if you ever seen those Dropboxes or those kinds of websites where you click a button and something happens, that's typically done using JavaScript, which runs in the browser. So yeah, any question about static versus dynamic? No? Okay, and I think that's our last slide. Caching is typically a strategy used by the servers or the browser to optimize these processes. So instead of having to go to the server all the time that you want to change a page slightly, if it's dynamic, or if you want to retrieve a new page that you've seen before or very recently, caching is sort of used to increase the performance of the browsers and sort of minimize the waiting times from clicking a web page or a resource in a web page till the moment something happens. Caching is sort of used to improve those times and make things more usable and more performant. Yeah. So one of the typical difficulties with caching is to determine whether local copy or how old a certain copy of the web page or a certain is, that it requires sort of a new version to be retrieved from the server. So this is done typically using an approach, but it's not really important what specifics of that approach, but it's typically one of the things that you need to do when doing caching. You need to determine whether the local copy can be reused or not. That can be done using the expires field in the header, though that's not always the case. So there can be some type of computation done, mathematical computation done, to determine whether it's time to re-update your cache or not. And sometimes the user can also force this updating of the cache manually by refreshing the page or asking it to revalidate the copy with a remote server. So in the way that does that is through a conditional get. So we have a request to the cache. The cache checks whether the content is expired or not, so that does a conditional get that allows it to determine whether it has been modified or not, and if it has been modified, then it asks for a new version of that web page, which is then sent and can be shown to the end user. So that would be the case where the cache needs to be updated. But yeah, long story short, this is sort of it for our application layer. So you just get a view of different protocols and different common applications used. And as a user, this is sort of the level you operate more and the kind of things you see when working with the internet. And any questions about this bit? Yeah.
When it comes to caching, is it storing the entire web page, or can it store just components of that web page? You've got a dynamic one.
Yeah, I guess you could think about a better way would sort of break that down into components. There could be different strategies, but yes, I guess if you have a very heavy web page with lots of resources, you could cache the resources individually and fetch them if needed. So if you have images, I guess your web page shouldn't have really sort of heavy images, but if it does, then caching those images will definitely improve the performance. Otherwise, your web server will sort of spend most of the time answering requests for those specific resources rather than the rest of the content of the web page of the HTML. So it's kind of a world in itself, caching and how to do it. So there will be different strategies depending on the page itself. But yeah, that's certainly one of the approaches taken when you have lots of things in your web page. Right. That's all for today. So Wednesday, I guess I wanted to ask you about Wednesday. We have different ways we can do our lecture on Wednesday. We can either run through the different courseworks together. Okay, I'm getting approving nods. We can talk about Linux, but that's not going to be in the exam, so maybe you're not too keen. Or we can skip altogether. But yeah, so I think coursework is the preferred. Yeah, okay. So on Wednesday, we'll talk a little bit about the exam, how the exam is structured, and then we'll sort of deep dive into the coursework. But I'll want to make it as interactive as possible, so I don't want to just come here and show you the solutions. I'd like you to kind of propose the solutions rather than me just handing those out to you easily. But otherwise, yes, Wednesday 9:30 a.m. we'll look at coursework 1 and 2 and sort of an outline of the exam and the format. But yeah, that's all for today. Thank you.